In this unit, we're talking about recursion and induction. And in the past, we've looked at sequences and found that some of them can be defined using recursion. And we did that last week in 6.2. In this section, we're going to look at some other concepts that can also be defined recursively. We're going to look at functions, sets, strings, and trees. We'll start by talking about functions. Sometimes functions can be written by using a recursive definition. So this example here, we have just this function that's been made up, and it's an example of a function that can be written with a recursive definition. So you see here what it starts out with is a starting value f of 1, and then for any value greater than 1, n greater than or equal to 2, and we're talking about all positive integers, then what we would do is we have to look at the value of the function at the previous integer in order to then come up with the value where we're at. So let's say that we want to find the value of f of 3. With functions that are defined this way, we can't go and just apply one little put the value that we want to find the function for, put it into one little expression and find the answer. We have to find each one as, from the very beginning. So if I asked for you to find f of 100, I can't go and just plug 100 into this function, because in order to find f of 100, I need to know f of 99 here. And then to find f of 99, I need to know f of 98, and so on. So it's not easy to find these functions unless you start at the very beginning. That's how you have to do it. So let's say that you were asked to find the value of when n is 3. So what is f of 3? So we'd have to start out first by looking at f of 1, and that's 5. Then for f of 2, we see that that's equal to f of the previous one, which is 1, f of 1, plus 2 times n, which is a 2. Okay, and that's equal to 5 plus 4 equals 9. This pen is working a little, is weird here. So I'm going to try to write a little bit better here. Hopefully that'll help. Anyway, so that's f of 2 equals f of 1 plus 2 times 2, which equals 5, plus 4, which equals 9. Okay, so now let's look at what f of 3 is equal to. So that's going to be f of 2, and then plus 2 times whatever 3 is, and in this, whatever n is, and n is 3. Okay, so now I have f of 2 is 9, and then I add 6, and I get a 15. Okay, so my answer would be f of 15. So let's look back up at this definition up here and see if now it would make sense what they say. They say in a recursive definition of a function, the value of the function is defined in terms of the output value of the function on smaller input values. So f of n is defined by f of n minus 1. n minus 1 is a smaller input value than n is. So that's what they're saying there. Now, we're really used to this when we talked about sequences. We did the very same thing, right? In sequences, we had we could say g sub 1 is equal to, we could write this whole thing just like a sequence. We could say, let's call it g sub 1 would equal 5. And then g sub n would equal g sub n minus 1 plus 2n. So that's exactly the same thing. It's just that what we're doing in this section is writing it in terms of a function notation, instead of sequence notation. But other than that, you're doing the very same thing. The factorial function is a function that can be written using a recursive definition. If you remember what factorial is all about, if I'm looking for 4 factorial, then that's equal to 4, starting with the number, then times 3, go down by 1, and go down by 1 again, all the way down to 1. So I have 4 times 3 times 2 times 1, so that would just be a 24. So that's how we get factorial values. And so, one way we could write this function out. We could say n factorial equals, and then we have n minus 1. We keep going down by 1 until all the way we get to 1. And then we're done, and we multiply all of those together. Now, that's not a really good definition for a couple of reasons. One is the reader is having to infer what's going on in there. We would hope that they understand that they're going down by 1 all the time, but that's not necessarily shown here. Another problem is that what if n is equal to 0, and it says that n can be greater than or equal to 0. So in the case of 0 here, we'd say we start with 0, we go down by 1 until we get down to 1, but we would already be below 1 to begin with. So what would happen there? That wouldn't really be a good, we wouldn't know what to do there. In general, let's remember what 0 factorial is. Just by definition, 0 factorial is equal to 1. So we really wouldn't use the same rules for finding 0 factorial as all the others, but that's just the definition. The factorial function is defined for 0, and it's just defined as the value of 1. So a better definition for the factorial function would be like something like this, where we first of all start by having the value of f of 0 be defined as 1. That way, that'll be taking, getting this 0 factorial equals 1 problem out of the way. And then from there on out, we're going to define the value of a function at n as in terms of the value of the function at the previous integer, and then just multiply it by n. And so that's going to be what we would use for n greater than or equal to 1. So this would be an example of writing that that function in using a recursive definition. At first, I think you might guess that, yeah, this would give us the same thing, but it'd probably be good to take a look and see what are some of the first few values of here, just to double check and make sure that this really is the same thing. So let's first of all look at f of 0. F of 0 by the definition is equal to 1 because we have that up there. Then f of 1 is going to be the value of n, which would be 1, times the value of the function at the previous integer, which would be 0. At 0. Okay, so it's 1 times f of 0. F of 0 is 1. So 1 times 1 is a 1. So we get a 1 for f of 1. F of 2 is going to be n, which is 2, times f at the previous integer, which is 1. And that's equal to, f of 1 was equal to 1. So we're going to have 2 times 1, and that gives us a 2. F of 3, we start with n, which is 3, times f at that previous integer, which was 2. And that's going to be a 3 times a 2, which is equal to 6. And then f of 4, 4 times f of 3. And that's equal to 4 times 6, and we get 24. So we see that that's how it looks like we are getting the same thing as if we were to use this more kind of just descriptive definition of the factorial function.
Now the book has you do a few problems where you're given a definition of a function and it's not in terms of a recursive definition, and they want you to write it as a recursive definition. So for this first example, we have a function called h, and it's defined as a summation. J is going from 0 up to n, and for each term will be j to the third. And so let's first write out a few function values and see, kind of get an idea what the pattern looks like, and then see if we can write a recursive definition for it. So first of all, let's look at h of 0. What would that look like? Well, that's j going from 0 up to n, and it's 0 to the third. So we just have one term, and it's 0 to the third. Okay, let's look at h of 1. It's going to start at 0, 0 to the third plus 1 to the third. H of 2 has 3 terms. H of 3 has even one more term. So you see that each time we get bigger, we have one extra term, and that this last term is the new one. So let's see if we could write a recursive definition here. If I wanted to just define what h of n is, let me do that again here. H of n, I could say that's defined as h of n minus 1, and then what? What would I, trying to make this look a little better here, because there's n's and h's and they're kind of looking the same here. So, okay, so here I'm trying to define h of n, and I want to define it in terms of h of n minus 1. So what's the difference between some value and the previous value? It's just that last term. So to get that from one to the other, we would just need to add that extra term, which would be the n cubed, right? So I could just go all the way up to n minus 1, which would still be getting all those cubed values. But if I stopped there, then to really get h of n, I need to add on that last term, which is n to the third. Okay, so I could say that for n greater than or equal to 0. Okay, so that's how we could rewrite that. Here's another example. G of n equals n factorial times 2. Again, let's write out a few terms here. So we've got g of, and it's not telling us where we're starting out on this one. So we can start with 0 since, normally it would say, for n greater than or equal to 0. So let's just assume that's part of it here. So let's look at, instead of starting at the really low levels like g of 0 and so on, let's kind of start out medium value. Let's look at a g of 10. That would be 10 factorial squared. And let's look and see what that would look like. 10 times 9 times 8 times 7, all the way down to 1. And then another one, 10 times 9 times 8 times 7, all the way down to 1, because it's squared. Okay, now let's look at g of 11. That's 11 factorial. And that would be 11 times 10 times 9, all the way down to 1. And then another 11 times 10 times 9, all the way down to 1. So let's think, how would we have gotten G11 if all we had to go by was G10? Well, the only thing that's missing from one to the other is this 11 here. And notice the 11 matches our n here. So we would try this and find out that it's true, that maybe we could write g of n as g of n minus 1, and then times what? What would we need to put onto this so that we would actually get g of n and not g of n plus 1? I mean, n minus 1. And that would be that last n value that gets multiplied twice, right? This 11 was there 2 places. And this is all multiplication, so we could just change the order and put all of those 11s, both of those 11s at the end. So then I'd say times 11 squared, but that would be an n squared, right? So that's how we could write that, and we could say 4, and we could double check, make sure it's true for the smaller values, and it would be, but this is what we would get for that. Okay, so it's kind of a matter of, on these types of problems, looking to see how you get from 1 based on the previous one, and then you can kind of come up with this recursive definition. Okay, now let's move on past functions and talk about recursively defined sets. So for a recursive definition of a set, we're going to always start with what's called the basis. So the basis would be, it explicitly states just one or more specific elements that are in the set. Okay, so it's going to say, this new set that I'm defining has these 1 or 2 or just a few little elements in there. Okay, it might be several, but it would start with this basis, and a lot of times it's just, only like 1 or 2 little elements that are a part of the set. But then it says there's a recursive rule there that says that you can, as long as you construct other elements in these certain ways, then those elements would also be in this particular set. Okay, so a recursive rule shows how to construct additional elements in the set from elements already known to be in the set. Okay, we'll see some examples here. And often there's more than one rule for that recursive rule, and we'll see that. And then there's the exclusion statement that says, basically, and then I'll read it, but I'm going to say it in my own words first, that anything that can't be constructed using that recursive rule, anything that can't be, start with a basis, something in the basis, in the sets told to us by that basis, and then constructed by using the recursive rule. Anything that can't be constructed by using those first 2, then would not be in the part as part of this set here. So here's how they say it in the book. An exclusion statement states that an element is in the set only if it is given in the basis or can be constructed by applying the recursive rules repeatedly to elements given in the basis. Okay, so again, start with the basis, have a recursive rule, and then say, unless you can get an element starting with the basis and then using a recursive rule or 2 or a few, then it would not be part of the set. And again, we'll see an example here real soon. But the last thing I want to say is that exclusion statement is kind of implied usually when we're defining sets recursively. So we don't usually say it. A lot of times we won't say, okay, anything that can't be constructed this way will not be part of the set. We'll assume that that's true. So a lot of times that exclusion statement won't be there. So it says here, since the exclusion statement is essentially the same for every recursively defined set, it's often excluded in a recursive definition of a set, but it is implied. So let's look at this example here. So we've got a special set, and basically it's going to be the set of all properly nested parentheses, okay? So, what would we mean by properly nested? Before we actually look over here at the basis, let's think about this. I would say that, and we're going to not worry about what's inside, we're just looking at parentheses, sets of parentheses. If I had a beginning parentheses and ending parentheses, and maybe something inside, but in this case, we're not even considering anything else, just parentheses. But if I saw that, I would say that looks like a decent set for a set of parentheses. We have a beginning and we have an end. Or I could put another set here, and that looks, good too. And, maybe I would have something like this. Like I could even have, when we use parentheses for things, like in mathematics, we could say parentheses here and parentheses here, like x plus 2, x plus 3, that kind of thing. And we see, yeah, two sets of parentheses like this would be okay. Sometimes we put something inside parentheses inside another set of parentheses like that. So maybe I would have something that looks like that. Now, again, all we're looking at are just parentheses, these strings made up of only parentheses. So we're not going to be really looking at mathematical, factors and things like that, okay? It's just these are strings of parentheses, and we're going to somehow be able to define by a recursive definition when we've got properly nested parentheses or not. And let me just draw something that would not be properly nested. Let's see, if I have, let's see, how would that work? Well, for one thing, that's not properly nested because I've got the right one first, and that we know that doesn't work. But I could also maybe have this and then like that. And that's not properly nested because I'm missing an end bracket, an end parentheses, right? We know instinctively, and just because we've used parentheses before, if you have a beginning parenthesis, you need an end parenthesis, and they need to be nested, and we can't have things like this where one of the left parentheses doesn't have a right parentheses. Okay, so anyway, we kind of know what we're supposed to expect here, but let's look and see how it's defined here. So it says here that the basis is the sequence right here, two parentheses, left one, right one. It's properly nested. So they're saying this is the basis that this is part of that properly nested set of parentheses, okay? This belongs in our set of all properly nested parentheses, okay? And we see that it is. It's a very simple one. Now, the recursive rule says that if we have two sets of strings that would be made up of parentheses, and if they're both properly nested, then here's two rules. If I put parentheses around either of those, then that would be properly nested as long as I put a left parenthesis and a right parenthesis like this. Or if I put the two together, they're saying that's also properly nested. Okay, so they're saying that you can get other things just besides this very simple basic left right by doing either of these things here. Putting two together, I could put two together like that, and that would be using this rule right here. Or I could start with this basis and then put parentheses around it, and that would be using this rule here. Okay, and then they have the exclusion statement, which again we can leave out if we, usually we will leave out, but in this case here, I've gone ahead and included it. The exclusion statement says a string is properly nested only if it is given in the basis or can be constructed by applying the recursive rules to strings in the basis. So anything else, like something up here, like these up here, would not be able to be constructed using this set of instructions. Okay? So let's think, how would some of these be constructed? How would this first one be constructed? Well, you could construct this in using these several times, but in different orders too. It's not always that there's only one way to get these. So I could say first that I'm starting with the basis. We always have to start with the basis, which is just one set of parentheses. Okay, so that's the basis there. And then I could say, then I'm going to use this first rule to put on an extra, put some other parentheses around it. Okay, so I could say that by using that first rule, by rule 1, I'll call this rule 1, and this is rule 2. By rule 1, it is properly nested. And what about this one here? Use a different color. That's properly nested because it's the basis. So if I put these two together, then I have this, and then I have this other one that I've already constructed. And I put them next to each other using rule 2. Then by rule 2, this is properly nested. Okay, because I put this one and that one together, and that's what rule 2 is all about. Okay, so that's what I would do to get that one. Okay, for this one here, I just start with 3 individual ones. Each of those are properly nested because they're both the sequence in the basis. And then I could say this is by rule 2. Again, I just put them right next to each other. Properly nested by rule 2. And then I could add another one on, because this is properly nested, I've just established, and I'm going to take a set from the sequence from the basis, which is another one of those, and again by another, also using rule 2, I would be able to say that those are properly nested. So hopefully you're getting the idea of this. This is kind of weird, is because basically you have to understand when you look at this that these U's and V's, these are just strings of parentheses, and so we can only do what any of these rules say to get something else that's properly nested. So we can either put parentheses around the outside of what's already assumed to be properly nested, already known to be properly nested, or we can just jam the two together, okay, which would be that rule 2. Now the book asks some questions like this. What was the last recursive rule applied in constructing each of the following properly nested strings or parentheses? There's only one I'm showing you, so we'll take out each of. So what was the last recursive rule? Now on these, you see sometimes there's more than one way. I could have, on this first one here, I could have done this first and that second, and then put them together. But I started with the other way. So the order isn't always, there's not only just one way to do it sometimes. But in all of the ones that they give you when they ask this question, there's only, it's obvious that there's only one way that for the very last recursive rule that could be used. So let's see if we can analyze this by going into the individual little basis values. So here's a basis here, here's a basis, and here's a basis. Okay, so it looks like that they put two bases together there, and then they put parentheses, this parenthesis here and that parenthesis there, by using that rule 1. And then they, over here on this other one, they used rule 1 again to put parentheses here. And so you see there, the only thing that's left now are those outer parentheses. So it looks like they, again, started with these 3 basis ones and then put parentheses around the first 2, parentheses around the second, put them together, which would be rule 2. And then the very last thing that would be done would have been to put that around in parentheses. So putting parentheses around that would have been rule 1. So I could say that's rule 1. If I had something like this, well, sometimes there's not a clear order, so I'm not going to try to come up with something because I'll probably come up with something that there's more than one way to do it. But the ones they give you, there's only, you would know for sure which is the last recursive rule used. So hopefully that makes sense. Okay, now we're going to move on to a different kind of set. It's still a set of characters, just characters, strings. They're calling it binary strings. So it says the set BK, or B to the K, where B is equal to, the set B is equal to 0 and 1. So 0 is an element of B, 1 is an element of B. B to the K is defined to be a set of all binary strings of length K. Basically, it's just saying anything that's a string of zeros and ones is going to be something that we could call B to some K here, and K is going to be represent the length of the string of length K. So basically, if I have a string of ones and zeros, then I would say that that is a binary string, and if I have 1, 0, 1, I'd say that that is in B to the 3. Right? Because it's a binary string and there's 3 of them. It's got a length of 3. Okay? 1, 0, 0, 1, 1. That I would say is in B 1, 2, 3, 4, 5. Okay? So that's all a string. Sorry, all a binary string is. But then they say the set of all binary strings without any restriction on length is denoted B star, and that's an infinite set. So B star just represents all of these different B's. So I could say that as long as it's a string of ones and zeros, it's in B star. We just don't care what size it is. So I could also say 101 is also not only in B3, it's in B star, because it's a string of binary, it's a binary string, and B star is made up of B's of all different lengths. And I could say 1, 0, 0, 1, 1 is also in B star. Okay, so that's all a binary string is. Now, they're going to start this, we're going to eventually be able to define this recursively. So because of that, they're going to talk about something called the empty string, which is just nothing there. And they're going to denote that by lambda here. Okay, so they say the empty string denoted by lambda is the unique string whose length is 0. Okay, so it's really an empty string. It's just literally nothing's in there. Now, B to the 0 would be the set of all binary strings of length 0, and there's only one element in that set, lambda, right? Because lambda is a binary string that has length 0, and there's no other binary strings that would fit in that category of length 0, right? So lambda would be the only element in b to the 0. Okay, and so if we wanted to see if we could come up with a way to denote b star without writing all of this here and, and assuming that we knew what b to the k is, then we could just say that it includes all of the b to the k for any k greater than or equal to 0. So, so one way we could write that then is b star is equal to the union of all of these different b's. B to the 0, union b to 1, union b 2, all the way up to infinity. Again, that's just like we've seen before, that's a definition that's not really that great because we have to use dots there instead of a real specific definition. So we're going to find a better way to describe this set without having to use those dots. We're going to find a way to define this binary string set, the set of binary strings, using a recursive definition. So this would be the recursive definition of b star. We'd say we'll start with the basis, the base case, of saying that lambda is in b star. Remember, the basis part is just saying we give, at least one element that's in the set, and then we give rules in order to come up with other elements that are in the set. So we'll say lambda is in b star. Then we say if something is in b star, anything, then this, then if x is in b star, then x0 is in b star. Now, what does this mean? So these are strings. So we're just talking about just adding a 0 onto the end of whatever x was. So it's just putting a 0 on the end. Okay, I'm going to just put that in words. We can put a 0 on the end, and that string is also in there. That string is also in b star. Okay? But then the next rule says, or we can just tack on a 1 at the end. So we can put a 1 on the end, and that string is also in b star. So if you think about it, any binary string could be constructed this way. We start with nothing, an empty string, and just repeatedly put in a 0 or 1 on the end, and we could get anything that we wanted to that we would already know is a binary string. So they have a little picture here of how would we create 101 from this. Well, we'd start with lambda, put a 1 at the end. But see, it doesn't matter if we're putting a 1 at the end. Lambda is nothing, so nothing with a 1 on the end is really just a 1, okay? And then we have this 1, and then we put a 0 on there on the end, and then we would put another 1 on the end, and then we've constructed 101, okay? So this is a great definition for constructing a binary string because we're using a recursive definition, and we don't have to use a lot of words, just these few little rules right here. Now, there's some other examples that they come up with that you have to work with in your challenge activities, and then also, I think, in some of the participation activities. So, some of these don't make a whole lot of sense. You just have to open your mind to say, okay, somebody's creating this set, and they've come up with these rules, and I'm just going to go for it, go with these rules and see what's in there. Okay, so that's kind of what you have to do. Okay, so let's just read through this and see if we can figure out. This is an example of what you will see in your book. So it says S is a set of strings over the alphabet A, B, star, for now that star is meaning it can be A's and B's, and it can be any length, okay? Just like we used star with the B's to say it can be any length. I think that's what that star means here. So we can have a bunch of A's, a bunch of B's, we can kind of mix them together, okay? That kind of thing. But it has to follow these rules, okay? So first of all, the base case, the basis is that lambda, again, at the empty string, is also is in S. So S is my set. Lambda is in S. A by itself is in S. B by itself is in S. These are characters. So you're looking at these not as like variables that represent numbers, okay? These are just alphabetic characters here. So A is in S, B is in S. Now, here's some rules. And only those strings that can be created using these rules would be considered part of S, okay? So the first one is if X is in S, so we already have something in S, then XAA is also in S. Let's just write that in words. We can add 2 A's at the end and get another element of S, okay? 2 A's, not just one, unless we have a rule further down that says you can add just 1 A. But this is saying, no, we have to add 2 A's for this rule. This next rule says we can add 2 B's. And it will also be an element. And there are no more rules, okay? So we start with an A or a B or nothing, and we can add 2 A's at a time at the end or 2 B's at a time. We can never add just 1 A. If I asked you, is B A B in S? You'd say, well, I would have to start with the basis of B is in S. Is there any rule that allows me to add just 1 A and then 1 B? No. I either have to add 2 A's or 2 B's, but I can't. There's no rule that would get me this. So we would have to say no. Okay? So what they ask here is list all the strings in S of length 3. Okay? So let's look. We have to start with something in the base case here. We could start with nothing and then add 2 A's or add 2 B's. But then we're going to continue add 2 characters at a time. So if we start with the empty string, we'll never get anything of length 3. Okay, because we have to add characters in sets of 2's. So our only choice here to get something of length 3 would be to start with, we can start with either an A or we can start with B. Okay, so let's start with A, and then we can use either of these rules. So I could have A and then use rule 1, AA. So that would get me one of length 3, or I could start with A and then add 2 B's. So those are 2 different 3 length strings, but I could also start with B and add 2 A's, or start with B and add 2 B's. So these 4 ways would be what you'd put in here for your, so you'd say A, comma, and I think it'll take any order, so A, B, 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 A, B, B, B. So those would be the 4 that would work for that example. Okay, so you just have to think about what each of these rules does and then say only follow these rules to get other elements in the set. Okay, here's another example. It's the same idea. We've got A's and B's. We're going to start with lambda or an A or a B. And in this case, what are we doing? Because these recursive rules are starting out by saying if X is in S, then what can we do to X? Okay, well, here, what they do, they put an A before it and a B afterwards. Okay, so we can, just think about what that is in words. We can wrap any element with A on the left and B on the right and get another element of S. And the other rule is the same thing. We can wrap any element with a B on the left and an A on the right and still get another element. And that's all we can do, nothing else. Here we're not writing out that exclusion statement, right? Okay, so now what are the strings that we can have of length 3? Well, if we start with lambda, I would just have an A, B. But I'm always going to have to add, again, like in this case 2, I have to add 2 characters at a time. So if I started with nothing and wrapped it with an A and a B, there'd be 2 characters already, and I could never get 3 characters that way. So I'm going to either have to start with an A. I could start with A, and then wrap it with an A and a B, or wrap it with a B and an A. Or if I start with a B, I could have a B in the middle and an A and a B, or the B in the middle and a B and an A. So those would be the different values of 4 different values for this particular set that has been defined recursively. Here's another example of a set that can be defined by a recursive definition. I think there's a couple of things that are misleading the way, this is straight out of the book, but they give you different variations of these questions. But this was very, I think, confusing. Well, it was to me, because they said arithmetic expressions, and we're talking about variables from this set. So when they're talking about multiplying 2 things together, I'm thinking that's multiplying 2 variables together like we've done all, we know how to do, right? And I'm thinking here when we're adding 2 together, that's just, saying A plus B. That would be adding 2 variables together, and then they have parentheses around here, which in regular mathematics is the same thing as if we drop the parentheses, right? Parentheses don't matter if we don't need them, right? We'd get the same thing no matter. So I was looking at these rules in terms of this is just regular kind of arithmetic. And what I found to be the case is that's not what they mean at all, okay? They don't mean normal arithmetic, and they're not talking about these being looked at as variables that represent numbers, okay? I think whoever wrote that was just very misleading. Basically, what in order to get the answers that they, in order to do it the way they want you to do it, don't look at that. These are strings. We're talking about strings, and so we're not talking about variables. We're talking about elements. Okay, every element of this set. So I'm going to do this. I'm going to cross out the word variable and say element, every element from the set A, B, C, D, E, F is in S, okay? So A is in there, B is in there, C is in there, okay? And yes, it looks like arithmetic expressions because they have a plus sign and a dot here. But they're literally saying to put a plus sign in between two elements, okay? And they're saying literally put parentheses around that. So just keep that in mind as we go further on this. So I just want you to know if you look at it as we're really doing regular arithmetic, that's not what this is at all, okay? So let's kind of try to interpret what this really is, what they really mean. So the base case, if we read it as every element from this set is in S, that's true. So A is in S, B is in S, C is in S, and so on. So those are that's the basis, okay? Then recursive rules. If we have two elements that are already in S, then here's what we can do. I'm going to start with the second one. We can put a dot between them. And that would be, put them together with a dot in between. Okay, so we can, I'm going to use the word concatenate. That just means, you know, putting two strings together with a dot between them. Okay, so we just literally put a dot between those two characters. This other one here says we can join them. We're talking about two established elements of S, so I'll just say them. We can join them together with a plus sign, but if we're going to do that, we have to slap parentheses around it. But we have to wrap that in parentheses. Okay? So for instance, let's just think of some things that we could do here before going on and answering this question. So I could start with let's just start with a C. That's in there because of the basis. And let's also start with a B. I could have, would be in there. C plus B with parentheses around there. That would be an element of the set. C plus B by itself, so I'd say that is in S. But this is not in S, right? Because I didn't put parentheses around there. And that's why it's so important to understand we're not just adding numbers together. Otherwise, we'd say these are the same thing, right? So if you're going to put a plus sign between them, you have to have parentheses. You can put them together with a dot. So I could have C dot B. That's in S. But if I put C dot B with parentheses around them, no, because it never says you can join them with a dot and then have parentheses around them. So that is not an element of S. Okay? So hopefully, you know, you kind of get the idea what that's all about. So then they say indicate which expressions are in S. Okay, so let's look at this first one here. Well, we've got A is in S, A is in there, and B is in there. We can join the two together with a dot. So yes, that's in S, right? A plus B. No, that's not, I'll put an X. No, because we can't put a plus sign in there unless we put parentheses around them. What about this? You might think, well, I ought to be able to get that by doing a couple of things. I can say A plus B, put that in parentheses. I could do that, but then see if I want to add a C to that, I could go plus C, but I have to put parentheses around that whole thing. Every time I put a plus sign, I have to put parentheses around there. So no, I could not get this because there's no way to get A plus B without parentheses right after the B. So that is a no. D times D dot E dot A. Well, I could do D, E, and A are all involved, all in that in S, and I could do this. But nowhere does it say I can put parentheses in there if I'm using dots. So no, I can't get parentheses from that. How about this one? This is looking promising here because I can start with A and B, join them together with a plus sign and parentheses around them. And then C is also in there, so I can put a dot, and then that would be in the set. I've joined two together with a dot. But if this is already in a set, I can join it together in the set with D, because D's in the set. So yes, this one is. This one here, B times C, we're never going to get that. You can't put parentheses around something joined by dots, so no. Here, yeah, we could get that, right? We have A and D are both parts of S, so we can put them together with a plus sign if we put parentheses around them. And then E is also in S, and we can put those two together with a dot. So yes, that's good too. So that's how we work with those. I'm going to do a few, let's see, I might do one more example like this before I'm done with this type of recursive definition. Okay, here's another example. We have similar to what we just did. In this case, it starts out the same way where we have these, and again, I wouldn't call it a variable. It's a character. Every character in this from this set here, A, B, C, D, E, F, is in this new set that we're just now defining called S. And then the recursive rules say that if we have two elements that are already in S, then we can put them together with a plus sign, or we could put them together with a minus sign, or we can put them together just one right after the other, but we have to have parentheses around them, okay? So let's see if we can figure out which of these would be valid expressions that would also fit in S. Could we get to this first one here by just using these rules? Well, we could get we know A and B are both in there, so we know that A plus B is in S, and we know that C is in S, so we could at least get this. We could put them together, but we have to have parentheses around them. So we could get that, okay? So that would be an S. But we can't get that last set of parentheses around there. There's no rule that says you can just slap a set of parentheses around anything. Okay, the only way you get parentheses in there is if you're putting it together with something else. So we would say no, that doesn't work. How about this? A plus B, that's in S, so that's good. And C is in S. Okay, I'll say that's in S, and C is in S. So we can put those two together with a minus sign using Rule 2. So we can say A plus B and then C, put a minus sign in between them, and that would be in S. Now let's go on to D. D is in S and so is E, so D minus E is in S. So here I've got two of these elements. I've got this thing here is in S, and this is in S. So by this third rule, I can put them both in parentheses, put them each in parentheses, and then put them right next to each other. So that would get me this here. So yeah, this is right. This I can get. That's in S. Okay? But now this next one, just like I did here, I could get A plus B minus C is in S, because I did that right above here. But nothing here says I can, again, just put some parentheses around anything. The only way to get parentheses if you're putting two things together. So no, that wouldn't work. This next one here, you know, we're getting better at it. We could kind of see right away maybe it's not going to work, but let's just start by saying A is in S and B is in S. So if we put an A in parentheses and a B in parentheses, put them next to each other by rule 3, that would be in S. So this is already in S, but now we've got to get this extra set of parentheses around it. And that's where, how are we going to get one set of parentheses around that? We can't. There's nothing, no rule that just will put one set of parentheses in there. So no way to get that extra set of parentheses. So no. Okay, so that's the kind of thing that you have to do in your challenge exercises. And again, you just have to, it really helps to write this out in words like we've done in the previous examples, where this says you can put a plus sign between two of them, two valid elements, and it's still in there, it's still in S. And you can put a minus sign between them. So these are literal characters we're putting here, and we're not actually doing, you know, that's a character we're just sticking in the middle of my two other strings. Here's a character I'm sticking in the middle, and here are these characters I'm putting in, you know, on each side if I'm putting two other elements together. So hopefully you understand that. If you're confused at all, let me know and I can go over it individually with you. I'd be glad to do that. Okay, so here's another example of defining a set by a recursive definition. Now this particular set has to do with a concept called trees. We're going to get into trees later on in the semester. So way towards the end of the semester, we'll be talking about trees. And in the book, they say we talk about trees elsewhere in the text, and that will come later. But they're at least going to talk about perfect binary trees here. So let me first tell you about a few definitions here. So a round circle is called a vertex. And then we have these little branches that can come off of those, and those are called edges. But then we can also have other little vertexes here, like this. So these straight lines are edges. And then we have vertex. Here's another vertex. And so on. Okay, so that would be an example of a tree. But we're going to find that it's not an example of a perfect binary tree, because we're going to find out those trees that can be created just using these rules here. Okay, so first of all, the basis of this recursive definition is a single vertex with no edges is a perfect binary tree. So just one little vertex. I forgot to say that the very top vertex is called the root. Okay, so one little vertex with just the vertex being its root there is in the tree. Yeah, I mean, sorry, is a perfect binary tree. So it's in our set that we're defining right here. The set of perfect binary trees. That's what we're defining. Okay, so now here's the recursive rule. If T is a perfect binary tree, so let's look over here, and this is just kind of like an outline of what the tree might look like. There might be more little, little things here and so on. So they kind of just have this triangular shape just to show that it's some tree. It's already known to be a perfect binary tree. So if T is this perfect binary tree, then a new perfect binary tree, T prime, can be constructed by taking two copies of T. So see, we're just taking T and making a copy of it, and then adding a new vertex V, and then adding edges between V and the roots of each copy of the T. So basically take this tree that we already know exists in this special set, make a copy of it and join it together with the vertex at the top. And then if we can come up with something, anything that we can come up using that rule, we would say that also is in our set of perfect binary trees. So you can kind of gather from this that perfect binary trees are going to be perfectly symmetrical, right? There's no way I could have gotten this tree from those rules. Because in order to have more than just one vertex, we need to have a mirror copy, an identical copy here. It's always going to be symmetrical here. Anyway, let's say, just so that you can get an idea, an example. What if T is this? Then what would T prime be? Well, we'd have T and another copy of T, and then put a vertex up there with edges between. So that would be what T prime is. Let's say if T is this, and that is a perfect tree because we just made it using those rules above there, then what would T prime look like? T prime is, we have that tree, and we make a copy, and then we put a vertex and join them together. So that would be T prime. Okay, so you see T is always going, anything in this set is going to be perfectly symmetrical like that. Okay, so now this is all you need to know for this section. I don't think there's any problems in the book that are going for this section that will be about these trees. However, in the next section, you're going to be proving some things about them. So you do need to understand about them. So in this section, you're learning about them, and then next section, you'll actually need to do something with this specific set that they've just defined here. Okay, so that is all that we needed to talk about for this section. So there'll be some participation activities to do and also a challenge activity to do. So just do those. Hopefully you understand this okay, so that next time for the next section, we can go on and start learning how to prove certain properties of all of these different things we've talked about today, prove certain properties using mathematical induction. And it turns out that's actually not very hard. probably learning about these sets like we did today is harder than actually what we're going to need to do in 7.2, which is then use mathematical induction. Because that mathematical induction probably won't take too much time, we will have to go on to some other sections too after that next time. Okay, well, good luck. Let me know if you have any questions, and have a good day.